Tommy, can you hear me?
Hello.
Hello, can you hear me?
Yes.
Okay, that's good. Let's see. Let's do some DAT practice problems, organic chemistry.
And you prepared some things?
I just looked up practice problems online,
Oh, okay.
uh and we could try these. And check the answers because I didn't do these yet. So we'll first have you try these problems and then like your thought process on it, and then if you get it, then we could submit it and move on. And then if you get stuck, then I could show you my thought process on this.
Okay.
Let's see. The dual order I heard is a big topic for the DAT.
Oh, really?
For organic chemistry. Like the DAT loves dual order questions.
Which two reactant would you use to complete the following reaction in high yield? Um, okay, wait, so on the product, the CO2Me, that's trans, so that
Mm-hmm.
means it can't be 4 or 5, so it has to be 6.
Mm-hmm. Yep, it has to be six, so we could eliminate everything that does not have six in it. We could eliminate A, we could eliminate D, and we could eliminate E.
Okay, and then let me see. So one, two, wait, 1, 2, 3, 4, 5, 6.
Hi, Tiffany.
I think you could use, wait, 1, 2, 3, 4, 5. 1, 2, 3. Okay, so yeah, we already know that.
Right, and that's the dienophile part, which is this part over here. For the diene part, what do you notice about the methyl group CH3s here? Like, are they cis, trans to each other?
Cis.
Yeah, cis, right. So for the diene, right, this is the general format for Diels order. We have a diene reacting with a dienophile, right? When they react with each other, there's a pocket that forms between them, which is this pocket right here. When they react, because the mechanism are like these electrocyclic arrows here, which would form this cyclohexene products here, right? Are you familiar with the endo rule, like endo rule, exo rule for the Diels order reaction?
I thought
How,
that.
like, I remember it, but I always got that
Mhm.
wrong.
Oh, okay. So for the endo rule, it talks about the stereochemistry for these products, right? Like how where the wedges are, where the dashes are. So I'm gonna show you what an out group is and an in group is for the diene. So looking at the dienophile, which is uh this part here, and the diene, right? Let's look at the diene. If you have a group coming out of the pocket, which are these groups here, and I'm gonna label them as O. Those are the out groups because they're facing outside of the pocket. If you have groups facing towards inside the pocket, then those are
So
called in
that's
groups.
endo.
Yeah, those are the in groups. Well, the endo and exo rule, we're not there yet. I'm just telling you the terminology and what the groups are before going over the endo and exo rule. Yeah, these are just terminology right now. right? This is not endo XO yet. I'm just showing you what an out group is and what an in group is, right? And then the dienophile. Do you know what kind of groups have to be attached to a dienophile to make the reaction rate go faster? EDGs or EWGs? Are dienophiles electrophiles or nucleophiles in the Diels-Alder reaction?
Wait, what groups have to be attached to what?
To
Dieno
the dienophile, right? Like what kind of groups will increase the Diels-Alder reaction rate? Like what kind of groups have to be attached to the dienophile, right? So a diene is going to be the nucleophile. The dienophile is going to be the electrophile, right? So yeah,
EDG, is it because they donating the electron into the nucleophile?
yeah, EDGs for the diene, right? The diene
Yeah.
is the nucleophile, so we want EDGs attached to the diene to increase the reaction rate. But for the dienophile, since we said that was the electrophile, we want EWGs on the dienophile to increase the reaction rate, right? Because EDGs donate electrons, like you said, which makes things a better nucleophile because negative charges are better nucleophiles, right? So we want EDGs on the diene. We want EWGs on the dienophile because the dienophile is the electrophile, not the nucleophile. And electrophiles are better when they are more positive charge, right? And they're more positive charge if there are EWGs on it because EWGs withdraw electrons. They take electrons from the dienophile. Which is why we see here the CO2Me looks something like this. Right. This is the CO2Me, and that's an EWG because if you look directly at the very first atom attached to whatever the system is, that atom is what is the partial charge of that atom? Let's say this was attached to a dienophile system like this. Right.
partial positive.
Yeah, partial positive. And if the very first atom is partial positive of the group, then that group is going to be considered an EWG. It wants to withdraw electrons to stabilize that positive charge, right? So that's an EWG right there. If the atom is partially negative, like if it was an oxygen instead, then that would be considered an EDG. If it's an R group, like any hydrocarbon chain, like a methyl group, ethyl group, isopropyl group, then that's also an EDG, but not by resonance, by induction, right? So let's just say that the dienophile can have some kind of EWG or some R group, right? It depends on what the dienophile is. Most likely an EWG. And these are just like vague positions because it most likely won't have 4 groups attached to it. It most likely will have like 1 or 2 groups attached to it only. Right? Where for the endo rule, which is going to be the major product, this is what you have to remember about this. The out groups are cis or the same side to the EWG, and the in groups are trans to the EWG, right? So looking at this product here, let's just draw the out groups as dashes. If the out groups are dashes, what would the EWGs on the dienophile have to be if we're following the endo rule? Like let's say we have 2 EWGs, like one EWG here and another EWG here. What is the stereochemistry of the EWG if the outgroups are dashes?
Wait, outgroups are cis to the EWG. So it has to be. Wait, what was your question?
Yeah, is it going to be a wedge or dash? Like
Dash.
from these, yeah, dash, right. because they want to be cis to the out group, right? Which we see the out group is dash right now. What are the in groups then on that diene? What are these in groups here?
Trans.
Yeah, so there are going to be wedges because they are trans, right? And every group that you see on these middle carbons here, like it could be any random R group, they will always, always, always stay flat and planar. There's no wedge or dash. And do you guys know the reason why these are always planar, flat and planar?
Because the
Like,
double bond.
yeah, the double bond. It's from an sp2 hybridized carbon, and sp2 hybridized carbons are always flat and planar. Whereas these carbons here are sp3, which we do have to include stereochemistry, right? So based on this stereochemistry here, what do you notice about these two groups here? They're cis to each other, right? Which means
Oh,
that
but then those EWGs are trans though.
those EWs are trans, which means that the dienophile would have to look something like this. One of the EWGs, right, is going to be this side. If we make a dashed line through this double bond right here, the other EWG would have to be on the other side like that. The other CO2ME has to be on this side right here. Right, that's what makes it trans. And then if this is trans, then you have to choose one to be your EWG. There's no more stronger EWG because they're the same exact EWG. If you say this is your EWG right here, then like that would have to be your EWG, right? Because your EWGs would be cis to the outgroups here, right? And then this other EWG right here is just trans to this EWG right here, which is this like trans alkene right here, right? But you notice how these two groups here are cis to each other,
Yes.
right? They both have to be an out group or they both have to be an in group. So which one of these dienes here show that we have the two methyl groups are both out groups or in groups? These ones are kind of harder to see because they're in the S trans configuration. We have to rotate them into the S cis configuration. So we could do that by rotating that single bond between them and getting this rotation here. Let's say we get, wait, hold on. Yeah. And this. Okay. So I just rotated this single bond right here to get to this point here. Right. This single bond is this bond here that I rotated. Right. I kept everything on this side the same, but I just rotated this downwards like that. Like, does that make sense on how I redrew this structure to get to this point?
Yeah.
Right. This point is already in its diene form, so we don't have to rotate that. But let's rotate this now. If we rotate this single bond right here, we're going to get that. Does that make sense on how I redrew this into this right here?
Yeah.
Right. Okay, so is this considered an out group or in group? This methyl group here.
That is an out group.
Yeah, how about this one?
In group.
And what does that mean? What is the relationship between them if we react them in a Diels auto reaction? Would they be trans or cis to each other?
Trans.
Trans. That does not match up with the products here.
Yeah.
Right.
So
So
it's
we get rid.
3.
Yeah, it's 3. Get rid of 1 and 2 because this is an in group, this is an out group. Whereas 3, these are both out groups here, right? Both out groups, they're cis. So the only answer here is C. Right. Well, let's check that. I haven't done this yet. But let's just see if we got it correct. Let's see.
Yeah.
Okay. Oh, nice. We got it. Yeah. Yeah. Right. So the most important concept that was tested here was the endo rule of the Diels auto reaction, where out groups are cis to the EWG and in groups are trans to the EWG. And out groups will always be cis to each other, in groups will always be cis to each other, right? Out groups and in groups are trans to each other. So out and in groups are trans. The dienophile stereochemistry here is just cis and trans. Like you said at the beginning, this is going to be trans, which is just that trans dienophile there, right? Okay, let's move on to the next one. Strongest acid. Let's see. Okay. How would you figure out this question here?
Cardio. Right.
Cardio.
Yeah, cardio or cario.
Right. Charge, atom size, resonance, dipole, dipole, interaction, ion, induction. Well, yeah, they go together, dipole, and induction. And then the O is orbital or hybridization. Okay, and then these right here, you use when comparing the conjugate base. Right? Because whenever you rank the strongest acid, the very first thing you do is draw out the conjugate base, right? And then the most stable conjugate base will come from the strongest acid, right? Because remember back in Gen Chem, strong acid gives a weak conjugate base. A stable conjugate base is a weak conjugate base, right? Because since it's already stable, it's not reactive. It doesn't want to react with anything. It's already stable, so that's why it's a weak conjugate base, meaning that it came from a strong acid. And then to determine the most stable conjugate base, you look at the CARIO acronym, right? Charge, atom size, resonance, induction, orbital hybridization. Okay, so let's look at one right here. What would the conjugate base of one look like here? Like what's the most acidic H in one?
CH.
Right, right. That terminal alkyne hydrogen right there, where when we deprotonate that with some kind of base, then we are going to get this conjugate base right here. Right. This right here is a CH3, where all the hydrogens are equal. So we're just gonna say this is the conjugate base of 2 right here. Right. Where some base is just gonna deprotonate this carbon by grabbing a hydrogen and giving that carbon a negative charge. This is the conjugate base of 2 here. Right. The conjugate base is just the negative version of the atom that gets deprotonated. Right. Ooh, okay. So for 3, this is a tricky one. What's the most acidic H here for 3? What would the conjugate base of 3 look like? Right. Think about which negative charge would be the most stable. Like which H would give you your most stable negative charge?
The metal on the top.
Yeah, that's right. The metal on the top. And do you know the reason why that's the most stable negative charge?
Resonance.
Yeah. This negative charge here can do resonance with the double bond. If we took one of the H's on the double bonds and got this conjugate base right here, this negative charge here cannot do resonance, right? Which is why this is less stable than this one. So that's good. Part of this question is identifying what's the most stable, most acidic H that would give us the most stable negative charge, right? For 4, all of these H's are equal, right? So it doesn't matter which H we take to get the conjugate base, right? But what do you notice about this negative charge here? Can this negative charge do resonance if it is on an atom that is already double bonded?
No.
Right, no, because that atom that's already double bonded, its p orbital is already occupied by the double bond, right? And if it's already occupied by the double bond, then that can't do resonance at all. So this negative charge here is localized. It's stuck. Localized. No resonance. Whereas this negative charge right here is delocalized because it's not stuck. It could do resonance here, right? This carbon here is not double bonded at all. And then for this one, it's very similar to number 2. Negative charge there. Okay, once we have figured out all of the conjugate bases, then we have to determine what's the most stable negative charge here.
So 3, because all the charges are the same, all the atoms are the same size, so it goes down to resonance.
Resonance, right? For 2 and 5, right? They're on an sp3 atom and they can do resonance, so like they're the worst acids ever, right? But for let's say 1 and 4, you notice how they can't do resonance? Like they can't do resonance at all. But they do have a different factor that makes them more stable than 2 and 5. What factor do they have that makes them more stable than 2 and 5?
Hybridization.
Hybridization, right? Or orbital. For 1, it's on an sp orbital. For 4, it's on a sp2 orbital. And do you know what is like going to be a more acidic H? SP, sp2, sp3.
SP, because more
SP.
S character.
Yeah, because more S character, right? And you have more S character, that means you're closer to the nucleus, right? And if you're closer to the nucleus, which is consisted of positive charges, that stabilizes the negative charge more if you're closer to the nucleus from the more S character. But there's something better than hybridization, which is resonance, which is higher in this choreo acronym ranking thing here. So get rid of 1 and get rid of 4, right? But if 3 wasn't there, what would be your answer if 3 wasn't there?
1.
Yeah, 1 would be the answer. But in this case, resonance overpowers hybridization. So the answer here would be 3. Oh, 1. Shoot, let's see.
Mhm.
Carb anions can be formed with the stability depending quite heavily on the hybridization state of the orbital containing the lone pair of electrons. Alkyne 1 is most acidic as the lone pair of the conjugate base is held in an sp orbital rather than sp3 or sp2. Having a greater proportion of S character, like we talked about, allows the electron density to be held closer to the positively charged nucleus, like we said, making it more electrostatically stable.
So they need
they're
workshop.
saying, let me see. Let me make sure. Let me make sure. Because I thought resonance overpowers hybridization. But I'll make sure. Let me search up pKa of terminal alkyne and pKa of allylic alkene. See which one's lower. Terminal alkynes, they get deprotonated typically. Oh, so the pKa of a terminal alkyne is around 26. The pKa of an allylic alkene is around 43. 26 is lower, so that's more acidic. Let me search up the reasoning why hybridization takes priority over resonance for this, because I always thought resonance takes priority over hybridization. Alkyne more acidic. Alkynes are more acidic than alkenes, which are in turn more acidic than alkanes because sp carbon atoms are more electronegative than sp2 carbons, which we said more S character, closer to positive nucleus, more stabilized. Oh, okay. I see. So, I got it. Let's see. Okay, so when you're comparing the acidity of this terminal alkyne and let's say this allylic hydrogen over here, right? The first thing you do is draw out the conjugate base, right? Which are these negative charges here, right? This negative charge is on an sp orbital, which has more s character closer to the nucleus. This negative charge here is on a sp3 orbital in both resonance structures, but this one can do resonance as well. But when we draw out that resonance structure, we see that the negative charge here is still on an sp3 hybrid orbital, right? Let's look at electronegativity induction here. The negative charges are on carbon, right? They're the same exact electronegativity. But if you introduce something like, let's say, a carboxylic acid, right? If we draw out that conjugate base, we get the carboxylate here, right? What is the hybridization of this negative charge on oxygen here? sp, sp2, sp3. Right, this is a little tricky because it looks like it has 4 things attached to it, but yeah, I'll see if you know the trick for this. Is it sp, sp2, or sp3?
sp3.
It looks sp3, right? Because there's 4 bonding groups attached to it. 1, 2, 3, 4. But the trick here is that if it can do resonance, right? And we draw its resonance structure, you're gonna see something else. Right? Let's look at that same exact oxygen here. What does this oxygen look like now?
sp2.
sp2, right? This oxygen in this form is sp3. This oxygen in this form is sp2. Because it could do resonance, it's going to favor the sp2 hybrid orbital form over the sp3, right? If you look at something like this, for example, this is sp3 because this oxygen here cannot do resonance at all. If it can't do resonance, then it's stuck as an sp3 orbital, right? Because it only has 4 groups attached to it. 1, 2, 3, 4. But if it can do resonance, then it's going to favor the sp2 orbital over the sp3 orbital because resonance is a stabilizing factor, right? So this oxygen here is actually sp2. So that could be another type of question, like what is the hybridization of this atom here, right? If it can do resonance, then it's sp2. If it can't do resonance, then it's sp3. Let me give you a similar problem to that. And they will most likely not give you lone pairs, so you have to like figure that out by the formal charges and everything. What is the hybridization of this nitrogen here?
sp3.
Yeah, sp3, because it only has 1 lone pair. And then like 1, 2, 3, 4 bonding groups, sp3. What about this nitrogen here?
So
Also,
this one can do the resonance.
Yes, it can do the resonance
oh,
because this pair of electrons here can hop down here and then pop this double bond onto the oxygen right there. If it can do resonance, does it favor sp2 or sp3?
sp2.
Yeah, sp2 hybridized, right? So this nitrogen here is sp2, this nitrogen here is sp3. So that's the difference between them, right? So you got to be careful here, right? So now if we compare like the stability of the negative charge of the carboxylic acid and this terminal alkyne right here, right? You know how in the last exam that we just did, they said that 1 is a more acidic molecule than 3 because of the S character. That's why the pKa of the terminal alkyne is lower than the pKa of the alkene. That's because of the S character here, right? We see that the negative charges were on the same atom, carbon. But what do you notice about the negative charge on this here, right? It's on an oxygen. Is it more or less electronegative than carbon?
More.
More electronegative, right? So it's more stable here. Even though this is sp2 hybridized, right? The pKa of a carboxylic acid is around 5, which is even lower than 26, right? So it's not always clear cut, like everything with resonance is going to be more stable than everything like over hybridization. It also depends on what atom the negative charge is on, right? We saw that the negative charge on all of these conjugate bases we drew earlier were on a carbon atom, right? And all those carbon atoms have the same electronegativity because they are the same atom. But if we introduce a carboxylic acid, even though it's sp2, which has less S character than this terminal alkyne here, the negative charge is on an oxygen, which is more electronegative. So that factor like makes it even more stable. Yeah. Okay, so the answer here is actually 1. 1. Right. Even though 3 can do resonance, it has a less S character, and the negative charge is on the same atom, carbon, which has the same electronegativity, right? But if 3 was like this, right? Then 3 would like be the more acidic one because the negative charge here is on a more electronegative atom, oxygen, compared to carbon. Right. Any questions on this one?
Wait, so when you do the resonance for 3, isn't it still the same?
Yes, if we do the resonance for 3, it's still the same exact structure, but the negative charge here, right? Oh, can you guys figure out what mistake I did based on what I just talked to you guys about? Like, what is the actual hybridization of this atom here that can do resonance?
SP2.
Yeah, sp2, right? Because if it can do resonance, it would prefer the sp2 orbital over the sp3 orbital. That's still less than sp here. The S character is still less than sp there, right? But that's only if we are we have to be careful. That's only if we have the negative charge right there, right? But if you have something like this right here, what is the hybridization of this carbon here? Can this carbon do resonance at all?
Like if there's
This
a negative
carbon.
there?
Oh, if there's nothing there, neutral. No pairs of electrons, no negative charge, no positive charge, nothing there. Just two invisible hydrogens.
No.
No resonance, right? And what does that give it? What hybridization?
sp3.
sp3, right? This carbon here that is allylic that next to the alkene is sp3 because it can't do resonance. But if we have a negative charge there, then that negative charge is sp2 now, right? In this example here, even though this nitrogen is neutral, that nitrogen has a pair of electrons that can actually resonate, making that sp2. Whereas carbon here has no pairs of electrons at all to do resonance, which is why it stays as sp3, right? Um, yeah. Yeah. So to summarize everything, hybridization takes priority over resonance if the negative charge right, is on the same atom electronegativity, but if the negative charge is on different atoms, then charge, right? Charge, which is the very top factor of Cario, charge takes priority. The number one thing takes priority. But they're all negative charges anyway, so that doesn't matter. It's gonna be induction, yeah, induction here, which has higher priority than hybridization. So induction takes priority over hybridization, where the negative charge prefers to be on the more electronegative atom. Like it prefers to be on oxygen rather than carbon. But if the negative charge is on carbons all throughout, we can't look at that factor anymore. We have to look at hybridization. Yeah. Any questions on this question?
I'm good.
Mhm. Okay, let's go to this question. Okay, nucleophilic acyl substitution. I'm gonna show you guys the general reaction for this. Right. Let's say we have a carbonyl attached to some kind of leaving group. It could be a halogen, it could be a carboxylate, it could be an alcohol, it could be an amine group, and some kind of nucleophile that floats around. Well, it depends on what kind of leaving group this is, right? Let's look at the more general one. Let's say this was a weak one, right? And let's say we are in acidic conditions, because there's also acidic basic conditions. There's actually a lot of factors here, but let's do the most common one. Let's do acidic conditions, H plus. Right now, this is an unactivated carbonyl. It's a weak electrophile, right? To activate that electrophile into a stronger electrophile, we have to protonate it using the proton source, like H2SO4, H3O plus, any acid, any strong acid. Once we have done that, this electrophile here is now activated. It's a bigger partial positive charge now. Because think of it like this. This oxygen with a positive charge is more greedy for electrons because it wants to be stabilized with a neutral charge now. Right? Once that's an activated electrophile, our nucleophile can now come in to attack that carbonyl carbon and then pop this double bond onto that oxygen right there. Right? When that happens, we get this tetrahedral intermediate right here, where this carbon is attached to the OH, which came from this double bond OH plus, which we popped the double bond into the oxygen, right? Because this oxygen before only had one pair of electrons. When we pop that double bond to give that oxygen an extra pair of electrons, that oxygen will now have two pairs of electrons like that, where it got its extra pair from this double bond right there, right? And then from here, there's a whole bunch of stuff, but let me just read the answer choices before going through the whole mechanism, because this is actually kind of long. Let's see. Which of the following statements is correct regarding nucleophilic acyl substitution. So we are looking for the correct statement here. Protonation of the carbonyl is followed immediately by loss of a leaving group. So is this true on what we did so far? Like after we protonated this carbonyl group, did the leaving group leave right away? Or did it stay?
Stay.
Yeah, it stayed, right? Because afterwards the nucleophile attacks the carbonyl. So get rid of A. It does not leave right away. SN2 reaction is the primary mechanism for the reaction. So do you guys remember the mechanism of SN2? What was the mechanism? How many steps were there for SN2?
1.
One, right? Backside attack. So it's not B because there's a lot of steps here. Ester hydrolysis proceeds in a single concerted step. So this is very similar to the last option. True or false? Wait, ester hydrolysis, think of it as a type of nucleophilic acyl substitution. It's not SN2. Not SN2.
Not SN2.
Yeah.
False.
SN1.
Yeah, it's false. Right. Because like a single concerted step would be like SN2, right? Because of the backside attack, it's just a single concerted step. But ester hydrolysis is a type of nucleophilic acyl substitution, which has many steps. Right. So that's false. Right. Loss of the leaving group is followed by carbocation rearrangement. So in this mechanism here, right, no carbocation at all is going to be formed because let me just complete the whole thing for you. Let's say the leaving group here gets protonated to become a good leaving group. Nucleophile. This oxygen here with the pair of electrons is gonna reform its carbonyl, kick out that leaving group. Nucleophile, leaving group, side product. Last thing here, some kind of conjugate base will just neutralize the carbonyl to get the neutral carbonyl here. So what we did in this reaction is substituted a leaving group with the nucleophile, right? This looks like an SN2 reaction because SN2, we always substituted a nucleophile with the leaving group, but it's not because the mechanism is different. It's not a single concerted step, it's a lot of steps here. Where are there any carbocations in this mechanism? Like any carbons with a positive charge?
No.
No, right. So get rid of that option. No carbocation is formed at all. What reactions do form carbocations though?
SN1.
Yeah, SN1 and E1 reactions, because the very first step is that the leaving group leaves, forming a carbocation. And then what do you always have to look out for whenever you form a carbocation intermediate in the mechanism? What is that one step that most people forget about?
Rearrangement.
Yeah, rearrangement, either a hydride shift or a methyl shift. That's the thing that people forget about the most. Right? This is not SN1 and E1, so get rid of that. So that leaves E, but let's just make sure it's actually true. Addition of nucleophile to the carbonyl is followed by loss of leaving group. Right, so that's true because once we added this nucleophile onto the carbonyl, right? What follows after that is kicking out this leaving group here. Right. So after the nucleophile gets added on, the leaving group gets kicked out. Right. So it is E. Okay, nice. Carbonyl compounds react with nucleophiles addition and forming tetrahedral intermediate. The tetrahedral intermediate itself can be, yeah, it could be depending on what carboxylic acid derivative is. It could be an acyl halide, anhydride, ester, amide. After the tetrahedral intermediate forms, it collapses, recreating carbonyl and kicking out the leaving group. Yeah, no carbocation formed at all. Okay, next one. What is your major? The heck? Okay. Well, shoot, this is gonna talk about chairs, chair flips, axial, equatorial. Okay, let's do it. Okay, so depending on this reactant here and reagent here, what reaction do you think is going to happen?
D2 catalyst replaces the H's with deuterium. No.
So it won't replace the H's with deuterium, but what functional group do we have here in the reactant? What is that functional group there?
Alkene.
Alkene, right? That alkene will get reduced into an alkane like that, right? The H's are still there. The original H's are still gonna be there. Right?
Oh, but it adds D's.
Yeah, right. Because D is an isotope of hydrogen. It's just another version of hydrogen, but you can't leave it as invisible. You actually have to draw them out like this. Right. But now here's the conceptual part, the tricky part of this question. For this reaction, think about the stereoselectivity. Is it syn addition or anti-addition? Do the D's attach on the same side of the alkene or on the opposite side of the alkene?
Same.
Yeah, same side, syn addition. I'm just gonna choose wedge. It doesn't matter. So if I chose wedge at that D, the other D has to also be wedge because this reaction is a syn addition reaction. And that makes the H's dashes like that. Right? Does that make sense so far?
Yeah.
Okay. So now from this point here, we don't have to do that redrawing into the chair conformer. We could just look at that fact, like they're cis to each other, and then eliminate the ones that are not cis to each other. Let's look at one. Are the D's cis or trans to each other?
They are, wait, one is up and one is down, so that means
Uh-huh.
it trans.
Trans, right? Because up, down, opposite side direction, trans, get rid of that. Because we know it's syn addition. How about two?
Also trans, because up and
Yep.
down again.
Mm-hmm. Three.
They're both down, so it's
Uh-huh.
syn.
Yep.
And then for 4, it's on the same carbon, but we know it's not on the same carbon.
Yeah.
So
Yeah, yeah, that's wrong. It's supposed to be on different carbons of the alkene, right? One for each part of the alkene. So 4 is automatically wrong. So it should be 3. Yes. Okay. Okay, nomenclature. Okay, try this one out here.
2 bromo, 1 chloro, 4 propyl, benzene.
Mhm. Let me know what you want to draw first, and I'll draw on the right side.
So draw the benzene.
And then you could also number it too. Like I'll just number it. Well, actually, yeah. Yeah, just let me know your thought process.
Add a chloro anywhere, so add a Cl anywhere. And then right next to it, add a Br. So, okay, so that's the numbering. So chloro is 1 and then bromo is 2. And then, yeah, finish that. And then for number 4, you add the propyl. So it's, yeah, 3. And that's it.
Oh, 3?
1, 2. No. Because the propyl's on the 3rd carbon, not.
Uh-huh.
So it's also not 2 because that's an ethyl group.
Uh-huh. Yep.
And 1, 2, 3. It's not 5 because they switched the bromo and the purple.
Mhm.
And then they switch the bromo and chloro for 1. So
Mhm.
it's 4.
Yeah, they just drew the purple group out weird, but it's the same purple group, right? Because if you rotate the single bond, which can rotate because it's a sigma bond, it's the same exact structure there. Nice, nice. Okay. Benzenes, my favorite. Okay. Rank the following aromatic compounds in order of reactivity towards electrophilic aromatic substitution, from most reactive to least reactive. Right. So electrophilic, yeah.
Okay, so we know that the benzene is full of electrons.
Mhm.
So to make it more reactive, you add more electrons inside.
Yeah, you add more electrons inside. And what groups can add more electrons inside?
Electron
EDGs?
donating groups.
Yeah, electron donating groups, EDGs. EDGs increase the reaction rate for EAS reactions. So remember back at that point I talked about, like look at the very, very first atom attached to the benzene ring. If it's partially positive, is that an EWG or an EDG? If it's partially positive, the very first atom.
Very first.
If it's partial positive, does
Then
it want
it
to
is
get,
withdrawing.
yeah, it's withdrawing. If it's partial negative, it's electron donating, right? And hydrogens, they're the reference point. Like that hydrogen is not an EDG nor an EWG. Right. Do you know what NO2 looks like? Like if we draw out in Lewis structure?
Positive on
Yeah.
the nitrogen
Right. Because it looks like this.
and negative on one of the oxygen.
Uh-huh. Right. And then if the very, very first atom, this is not partially positive, it's fully positive. So that makes it a very strong
Withdrawing.
EWG, right? And think of it like this for EAS reactions. EWGs are deactivators of the EAS reactions. And EDGs are activators. They activate the reaction rate. Right. So automatically, what's the one that's the least reactive?
NO2.
Yeah, 1. So let's get rid of D and E, because 1 is at the very last for ABC. Okay. Another factor, right, is going to be electronegativity. So let's talk about electronegativity here. Let's say we have this benzene ring compared to this benzene ring here, right? Do you know which one's a stronger EDG and why? If that, I could explain too.
EDG.
Yeah. So
Okay,
think
so
about
oxygen is more electron negative than
yeah.
nitrogen. So what does
Uh-huh.
that
Right. So that is the factor that I wanted to talk about, electronegativity. If oxygen is more electronegative than nitrogen, does it want to keep its electrons more or
mean? It keeps it.
get rid of it? It keeps it more. So does that make it a stronger EDG or weaker EDG? Can it donate that electron as much or no?
No.
No, right. So more electronegative atom means weaker EDG. Less electronegative atom means stronger EDG. So based on that case, a less electronegative atom is a stronger EDG. It activates the the benzene more. It makes it more negatively charged. Right. Okay, so I think you could finish the rest here.
So 5 is a EWG because the partial positive from the carbonyl.
Uh-huh. Well,
And
from that point, you could just already automatically choose the correct answer. Like we just gotta find the two deactivators, and then if you know like the other ones are like actually what
it's
is
a
this? What
A.
is this here? Yeah, yeah. Right. It's A. Right. Because what is this group here? Is this an EDG or EWG, and why?
EWG. No, EDG because the oxygen has lone pairs.
Uh-huh. And it's also partial negative. It has lone pairs and partial negative. Right? It has lone pairs for it to donate into the ring, so it's an EDG. So the only EWGs here are 1 and 5. They have to be the lowest. 1 and 5. The reason why 1 is a stronger EWG is because of this full positive charge there. We could eliminate B and C because they don't have that at the bottom too. But let's just make sure everything else makes sense. 3 is the most activated because that nitrogen there is partial negative and it has a pair of electrons. 4 is next because it also has a pair of electrons and a partial negative charge. But what's the reason why 3 is stronger than 4?
Because nitrogen is less electron negative, so it's able to donate the electrons more than oxygen.
Uh-huh. Yeah, more willing to donate electrons than oxygen. Oxygen is more greedy. Nitrogen is more willing to donate. Right. And then 2, that's the one in the middle. It's not an EDG, not an EWG. Right. Okay. So we said it was A. Yes. Okay. There are two main electronic effects: resonance, EDG, and inductive effects, which is the electronegativity. Yeah. Okay. Okay. Okay, zero dipole moment. Which of these conformations have zero dipole moment? Or in other words, all the dipole moments cancel out to a net zero dipole moment.
3.
Yeah, 3, because the electronegative atoms here, they would cancel each other out. Right, 4, they would add. So nope. 2, they would add. Nope. 1, they would add. Nope. So 3. Nice, nice. Okay. Yes. Yeah. Anti-paraplanar. Right. This is anti. Do you know the other names of the Newman projections? Like, what's the other common name for a conformer?
Gauss.
Gauss, right? Yeah, and that's basically it.
Eclipse.
Yeah, eclipse is a type, right? Eclipse. And what was the other one that's not eclipsed? Where they're
Gauss.
more separated. Gauss is a type of the other one. Gauss and anti is a type of the other one. It's actually the S. And rhymes with dagger.
Stagger.
Staggered, yeah, staggered.
Oh, stagger.
Staggered. But there are two types of staggered, gauche and anti. But eclipse, there's no like name for a specific eclipse. There's just specific staggered. Yeah, staggered and eclipse. Where let's just talk about the stability of these. Which one of these is the most stable? Well, first, which one's more stable, staggered or eclipsed?
Staggered.
Yep, staggered. So now, which one is more stable, staggered, anti or gauche?
Anti.
Anti, yeah. So anti, gauche, which these two are staggered, and then eclipsed is less stable. Right, so stability goes from that direction down to up. Least stable is eclipsed, any eclipsed, and then staggered, where anti is the most stable. Well, there is like more things about eclipse, but I don't think that's too specific. That's I don't think that's gonna be tested. Okay, so let's see. Okay, let's do this one. Paste. Okay. Which of the following compounds gives 3-methyl-2-butanol upon reduction with LiAlH4, lithium aluminum hydride? So first, let's draw out what this thing is. 3-methyl-2-butanol. What would that look like?
So butanol. Draw 4 carbons in a chain. And then on the second carbon, add an OH. And then on the third one, so the one next to it on the right side, add a methyl. And that's it.
Yeah. Nice. We're trying to get to this.
And
ALH4.
LiAlH4 is a weak reduction, right?
It is a reducing agent, and it's a strong reducing
Oh,
agent.
strong.
What's the weak one? There's another one that's a weak one.
PCC.
NABH4.
Yeah, NaBH4. NaBH4.
Oh.
NaBH4 is a weak reducing agent. Right. What can NaBH4 reduce? Like, what can it not reduce since it's weak?
It can't reduce carboxylic.
Uh-huh. Yeah.
Amide.
Uh-huh.
Amide.
Does it have to do something with the substitution?
Ester.
Ester, yeah. Ester, and then
Like the substitution of the alcohol or no?
It's not the substitution of the alcohol, but the reactivity of the carboxylic acid derivatives. Are you guys familiar with the carboxylic acid derivatives like acyl halide, anhydride, the parent carboxylic acid, ester, amide, nitrile? Those derivatives?
Yes.
I'm good with those.
Oh, wait, you're good with it, or you're not good with it?
Oh, I'm good. I'm good with those.
Oh, you're good with those. Okay, okay, yeah. Wait, so these ones and nitrile, right, which is a cousin derivative, can't be reduced by weak reducing agent, right? What NaBH4 can only reduce are 4 things. It can only reduce an aldehyde, a ketone, and the top 2 most reactive derivatives. What are the top 2 most reactive derivatives? Carboxylic acid derivatives. Like the most reactive derivatives.
Acid halide.
Acid halide is the top one. There's the one below that.
Acid anhydride.
Yeah, acid anhydride. Right. Because these are very reactive, it allows for the weak reducing agent to reduce it. Right. But the weaker ones, like the original carboxylic acid, amide, ester, nitrile, those are the weaker ones. Those don't allow the weak reducing agent to reduce it. Right. LiAlH4 can reduce everything. It can reduce all of this and all of this. Okay, so moving back to this question, of which one of these, when reacted with LiAlH4, would give this here?
One.
It's a ketone because it's secondary.
Yes, ketone. Right, and Tiffany's right. It's 1 because we have 3 different ketones here. We have 1 ketone, 3 ketone, and 4 ketone. And Tiffany chose the right one. 1. Why is it not 3 or 4?
Count carbons. That's what I was taught.
Yeah. This one has
Wait,
1,
but
2, 3,
it can
4.
reduce all of that, but we just have to know like which is the right structure, right?
Yeah, yeah, it can reduce all of it. We just have to know which was the right structure.
So yeah, 1 because the OH is, or the carbonyl is on the second carbon, and the
Yeah.
OH is on the second carbon.
Right, right. 1, 2, 3, 4. Which is this 1, 2, 3, 4. Right. Can it reduce 5? Wait, it can reduce 5 because it's LiH4. But what would it look like if it reduced 5?
Um,
Like,
carboxylic acid?
yeah, so
Aldehyde?
ester will go all the way down to an alcohol, where the
Oh,
carbonyl carbon here is the
Oh,
carbon that's holding the alcohol, like that. Right. Um, it does go through an aldehyde intermediate, but it doesn't stop there because that aldehyde can get further reduced into the alcohol. What would this aldehyde look like if it gets reduced by LiAlH4?
primary
Mm-hmm.
alcohol.
Yeah, primary alcohol as well, where that carbon there of the carbonyl is the carbon holding the alcohol, like that. Right. But that's not what we want. We want this, which is 1. Okay, let me give you guys another tricky one that might show up. What would this look like if we reduced this with LiAlH4 followed up by acid workup, proton workup, acid workup?
Amide, and you said amides can reduce everything.
Lithium aluminum hydride can reduce everything, including amides. Okay.
Oh yeah, that's what I meant.
Amide not reducing.
So
I don't remember exactly, but it was something like with the ends in it, like there was an N in
Uh-huh.
it too. It doesn't go
Yeah.
oh, is this the imine and
Oh no, no,
imine?
no. No,
No.
that's something else. It's not imine. This is reducing, right? And when you're reducing an amide, you just get rid of the carbonyl and get an amine. Amine. Right. If you have something like this, then your amine would look like this. All you're doing is getting rid of that carbonyl. Another thing could be something like this. Nitrile. Have you guys learned about reducing nitriles?
Um,
No, but I think I saw it. Mm,
I think
Yeah.
I think we
I think
have
it go
learned
to
it, but
NH2.
Yeah, it does become NH2. But I'm gonna
Oh,
give you two structures. A common one that people draw from this, and then the other one, which I'll ask you guys which one's the correct one. Is it this NH2 or this NH2?
I'll take the latter one. This,
Uh-huh. Wait,
yeah, that one.
just
this
Because
because,
one.
three carbons for the other one, while the
Yeah,
first
yeah.
structure has 4.
Right, right. Right. A lot of people forget about that extra carbon of the nitrile right there. Right. Don't forget about that. Don't forget. Right. This one has 1, 2, 3, but we had 1, 2, 3, 4 carbons, which this one has 1, 2, 3, 4 carbons here, which is gonna be this one here. Right. It's not this one. Right. That's a common mistake that people make from reducing nitriles. They miss that carbon. So for this one, it's gonna be that, not this. Because this carbon here of the nitrile is that carbon right there. That carbon of nitrile is that carbon right there. Yes. Okay. Yes. Nice. What the heck? This looks so weird. Let's see. This is going to be about stereoisomers. Let's break it down. Consider the molecule below. If the CH3 and Cl groups were switched with each other, how would you describe the new molecule relative to the one below? CH3 and Cl switched. So let's draw that out. Okay. Oh yeah. I'll have you guys think about this and try it.
Wait, do you switch the wedge and dash too?
Oh no, I do not. Wait, hold on. We're switched with each other. No, you don't switch the wedge and dash. Maintain the stereochemistry. Just switch the groups, right? So the Cl that was dash now becomes a wedge. The CH3 that was a wedge now becomes a dash.
It is. Wait, if it's diastereomer.
And why?
Because even though those two switch wedge and dash, the H and the CH2 and H3 at the bottom didn't switch.
Yeah.
Not all
The
the
only
stereo
chiral center.
centers.
Yeah, not all of them change. Only this one that I starred change. This one at the bottom, no change. Right? Some chiral center change, but not all chiral center change. Diastereomers. What would it have to be if they are enantiomers? Like, what
All
would
of them
the
changed.
yeah, all of them change for them to be enantiomers, right? If nothing changed, then they're identical, right? They're the same thing if nothing changed. Nice. Yes. Yeah, I didn't want to do the R and S thing because that takes a while, but we didn't need to do that to get the answer. The important concept that was tested here was how many changed. Like did all of them change or not? Right? But you didn't need to do this R and S stuff because they didn't ask for R and S. They just asked for the relationship diastereomer enantiomer, which all we had to know was some changed but some did not change to get the answer. Copy. Paste. Okay, so which one of these reactions follow the anti-Markovnikov rule instead of the Markovnikov rule for alkene reactions?
Hydroboration oxidation.
Yeah, hydroboration oxidation, right? The rest follows Markovnikov: hydration, oxymigration, demigration, addition of HCl, addition of Br2. Yeah. Can you remember one more reaction that does anti-Markovnikov for alkene? I'll give you a hint. It has to do something with D, right? HX and something else that goes with it to make it anti-Mark.
Oh, peroxide.
Roar or H2O2. Yeah, peroxide. Yeah. Okay, that's it. Do you guys want to do something else, like more practice, or any questions you guys have?
Can you go over the mechanism for Wolff-Kishner? Because I saw that on my practice test and I forgot the mechanism for it. Even though I don't,
Oh,
yeah.
that was tested for the DAT, the mechanism of Wolff-Kishner.
No, not the mechanism, but then It just
Oh, the
helps.
reaction.
Yeah.
Okay, the mechanism, I highly doubt it's gonna be tested because it's really long. There's like two big steps there, but we could go over that. I'll show you what to recognize for it and what
Yeah.
to do to predict the product, and then we could go over the mechanism if you want still. But the mechanism is pretty long,
No,
right?
okay, no, no, just like the main part.
The the main part, okay, and then figuring out what to do from there. Right.
Yeah.
So Wolff-Kishner reduction. This is a reduction reaction. So for this reaction, you're gonna have a carbonyl that goes down to an alkane. Right. And then for the reagent, you're gonna see I see it in multiple forms, but here are the three forms that I've seen it in. H2N NH2 or NH2 NH2 or N2H4. Right. All of these are the exact same thing, but I've just seen them in different practice problems. You will see this with a strong base like KOH. You can also see it as NaOH with heat. Uh, you might see water there as well. Okay, so just recognize these like two N's with four H's, N2H4, or NH2NH2, or H2N base and water with heat. Then you know that this is a signifier for Wolff-Kishner reduction. Which what you're gonna do is find all your carbonyls and get rid of it, cleave it. So some examples. That's it. Right, just get rid of that carbonyl, carbon number one oxygen. Right, it will overreact. It doesn't react with only one carbonyl. It would react with all the carbonyls. So all the carbonyls here would be reduced down into the alkane like that.
Oh,
Uh-huh.
okay.
Yeah. Right. Was that the answer for your practice that you did too?
Yeah, it was
Okay.
that- okay.
So the double bonds of the alkene stays there, right? It doesn't get reduced. The only thing that gets reduced is the carbonyl. These alkenes on the benzene ring stays there. Even if it was an alkene that is not aromatic, that's not part of a benzene ring, that will also stay there, right? Because this only targets carbonyls. It doesn't target alkenes, right? So the alkene there stays unreacted, no reaction there. Get rid of the carbonyl. So this reaction just eliminates carbonyls.
Okay.
Uh-huh.
And can you also go over the Claisen condensation?
Yeah, Claisen condensation. Let's go. So here are some general things about this reaction. The nucleophile is always going to be the alpha carbon of an enolate ion. The electrophile is always going to be the carbonyl carbon of an ester, right? Where the alpha carbon of the enolate ion, it could come from an alpha carbon of a ketone or an ester. The electrophile always has to be a carbonyl carbon of an ester. The product is always a 1,3 dicarbonyl. Something like this. where we have two carbonyls that have a 1,3 relationship with each other, right? 1, 2, 3, 1,3 dicarbonyl. Right. The intermolecular version of this, there's a name for that. It's the Dieckmann condensation. But for the intermolecular one, you always look for the nucleophile that would make the most stable ring, right? Because all intermolecular reactions, they always make a ring, right? Because do you guys remember what it means for a reaction to be intermolecular? Like what does that mean for a reaction to be intermolecular?
Reacts with itself.
Yeah, it reacts with itself, it attacks itself, where the nucleophile is on the same molecule as the electrophile. And when it reacts with itself, it always forms a ring. Same molecule as electrophile. Reacts with itself. Reacts with itself. Always. All intermolecular reactions always forms a ring. Okay, let's look at a simple example first. There's different types of Claisen. There's self Claisen, there's mixed Claisen, and there's intermolecular Claisen or the Dieckmann. So let's do the simple one first. Self Claisen. Let's say we have this ester here, right? We said the nucleophile was the alpha carbon of an enolate ion. What reagent is needed to create an enolate ion from the structure here? What even is an enolate ion? Do you guys remember the functional group of an enolate ion?
It was an enol, but there's a negative charge on the oxygen.
Yeah, an enol, but a negative charge on the oxygen there, right? Where we want to make this carbon here negatively charged somehow. What kind of thing do we have to add to make this carbon negatively charged? Right, I'll give you guys a hint by drawing out one of the invisible hydrogens here. Right. What can we do?
You need to deprotonate it so that
Yes.
you add a double bond in between that carbon with the H and the carbonyl carbon, and then you kick on, or yeah.
Yeah, we pop the double bond onto the oxygen to give that oxygen a negative charge, forming the enolate ion. And there's a very specific base that we need to use. It can't be any random base for Claisen. What specific base do we have to use for Claisen? Right. Think about this OR group of the ester.
Is it that group but with the negative?
Yeah, it's this exact group, but a negative charge on the alcohol. Like that. That's the exact base we want. Right. This is the thing that is going to react. You might see it in different forms. You might see it as NaOCH2, CH3, and then the solvent CH3, CH2OH. Or instead of Na, you might see it as K, because those are spectator ions. Whenever you see K or Na, they're always positive charge, making whatever is attached to it a negative charge like this right here. But that's the exact same thing right there. That's the exact specific base we need for Claisen condensation reactions, right? That's gonna form the enolate ion. Wait, my MacBook is 10%, so I'm gonna be back. I'm gonna get my charger really quick.
Joseph, how do you remember this? It's crazy.
I'm surprised that I remember it, and I didn't even finish studying OChem too.
Like No, but then you've been scoring really well in OChem, right?
I've been scoring okay.
No, like, what was the latest test? What did you get for OChem without studying at all?
19.
Okay, that's good. I studied a lot for OChem and I got 20. But then your first one, you got a 22?
I got 20. 22 was Gen Chem.
Oh, crazy.
I know Joseph's taking it again July 8th. Is this your first time taking the DAT, Tiffany, or
I wish. I
We
wish.
took it together the first time. We're gonna take it together the second time.
wait, isn't this your third time, host Joseph?
Yeah.
This is my second.
uh,
Are you also
no.
pre-dental or?
I'm going to chiropractor school, so not pre-dental.
Oh, okay.
Chiropractor, yeah. I'm starting this summer, yeah.
Do they require like the test require OChem for you guys?
So for chiropractic school, there's no standardized test, but I was pre-med before, which the MCAT did require OChem, right? And a lot of like pre-health professions required OChem, like pre-dental, pre-med, pre-PA, pre-pharm, pre-vet, pre-nursing, like all those health fields, they require OChem. But there's no standardized test for chiropractor, so they didn't require OChem.
Oh, okay.
Yeah. But yeah, I just like do my own like OChem tutoring on the side because like I just wanted to do continue tutoring. I already graduated UC Davis, so I don't tutor for them anymore. I just tutor for myself, like from other schools.
Oh, okay.
Yeah. Uh-huh. So the first step of the mechanism for this Claisen condensation here is to deprotonate this alpha hydrogen, which is the most acidic hydrogen, right? Because what did we say at the very beginning of the session here? What does the most acidic hydrogen give? Like what kind of conjugate base? A stable conjugate base or an unstable conjugate base?
Stable.
Yeah, stable conjugate base, right? And what is the reason why this would give us the most stable conjugate base here? Like if there was a negative charge on that carbon, what's the reason why compared to this negative charge over here or here or here?
Resonance.
Yeah, resonance, right? So that's the reason why that's the most acidic hydrogen, the alpha hydrogen. Right. So first step of the mechanism, form that enolate ion. Right. Now, what's the nucleophile at this point here? Is it this O minus or is it this alpha carbon? And why?
The minus.
Yeah, so O minus looks like the nucleophile because you see the direct full on negative charge there, right? But if we look at the resonance structure, here, the negative charge moved to the carbon. Which negative charge is less stable? The negative charge on the oxygen or the negative charge on the carbon? Which one is less stable?
Less stable. The one on the oxygen
Carbon.
carbon.
Right, and why? And why? Why on the carbon?
I don't know.
Because carbon is less electron negative, so
Uh-huh.
it can't hold the electrons as well as oxygen.
Yeah, right. Carbon is less electronegative than oxygen, so that's why it's less stable. Right. Less electronegative, less stable. And if it's less stable, does it mean that it's more reactive or less reactive?
If
Like
it's
if it's less
More.
stable.
more
More.
reactive.
Yeah, more reactive or nucleophilic. Right. Oxygen minus, more electronegative, more stable, less nucleophilic, less reactive. Right. Which is why the alpha carbon here is the nucleophile, not the O minus here. Right. Because of this resonance structure here. Yeah. But when we usually draw the mechanism, we don't usually draw out the other structure. We usually just draw out that reforming the carbonyl and then using the alpha carbon to attack whatever electrophile. Right. So I'm just gonna redraw that enolate here, where we know that the nucleophile is gonna be this alpha carbon. So I'm gonna star that alpha carbon right there to represent the nucleophile. Since this is a self-Claisen condensation, I'm gonna bring in another version of itself of the reactant here, right? What did we say the electrophile is for Claisen condensation reactions? What is the electrophile?
Carbonyl carbon.
Yeah, the carbonyl carbon, which is going to be that carbonyl carbon right there, right? So this is the nucleophile for the reaction. This is the electrophile for the reaction. When we go back down to reform the carbonyl, that alpha carbon there is going to attack that carbonyl carbon and then pop that double bond into the oxygen right there. Right. It might be easier if you use this resonance structure because it's more easy to see like this negative charge going directly to attack that carbonyl carbon right there, right? That's the same exact thing that's happening here. That negative charge there on the alpha carbon is attacking this carbonyl carbon here. But we usually draw in this form because this is the major resonance structure here, which actually exists, right? But this is actually what's happening. The alpha carbon here is attacking, not the O minus. Right? Does that make sense so far?
Yeah.
Yeah. So now this next part of the mechanism here is the trickiest part. Connecting the two pieces together, right? So I'm gonna draw out the nucleophile like this. And the methyl group is gonna go down like that. And then the nucleophile is gonna be that star carbon right here. And then I'm gonna draw the new bond out in blue. That's the new bond right there. And that's the electrophile right there. This is the new bond between them, between the star and dot. Right? That new bond was formed from this attack right here. Now I draw whatever is attached to the dot. The dot is attached to a single bond O minus now, no longer a double bond O because we popped that double bond onto the oxygen, giving that oxygen a negative charge. It's attached to an ethyl group, which is this ethyl group here, and it's attached to an OR group, which is this OR group there. Does this make sense so far?
Yeah.
So now the next thing here is to reform that carbonyl and then kick out this leaving group here. But previously, what did you learn about this leaving group? Is this a bad or good leaving group here?
Oh,
Bad.
Yeah, OR is a bad leaving group, right? This OR is a bad leaving group. OH is a bad leaving group. R is a bad leaving group. H is a bad leaving group, right? So technically, this is your final answer already. But if you draw out the mechanism, that wouldn't be correct. If you're just trying to predict the product, then you just end here and then say that's your final product. But for the mechanism, that bad leaving group is gonna go back for its vengeance and deprotonate the alpha hydrogen in between the two carbonyls here, make the enolate ion, and then that becomes an ethanol alcohol there. Now, the last step, acid workup, some kind of acid source, is just gonna protonate the alpha carbon, reform that carbonyl, that alpha carbon picks up a proton to just go back to that carbonyl that we had earlier, right? Which is why this is another conceptual thing that might be tested on the DAT for Claisen condensation reactions. They require at least 2 alpha hydrogens to go through, right? The first alpha hydrogen is used to form the enolate ion. The second alpha hydrogen is used to quench the bad leaving group, right? We need at least 2 alpha hydrogens for the Claisen condensation to go through. If we only have 1 alpha hydrogen, no reaction would happen. It goes backwards, retro Claisen. if we have 3, then that's good. Like that's at least 2. It can go through, but we need at least 2, right? Where we see in the mechanism here, this was the very first alpha hydrogen here that was used to make this enolate ion here. Right. This is the second alpha hydrogen right here that used to quench this bad leaving group here. Right. If that second alpha hydrogen was not there, then that bad leaving group would just go attack that carbonyl and go all the way backwards, no reaction, right? So that's an important concept. Glycine condensation needs at least 2 alpha hydrogens to go through. Where we see in our final product, right here, this is a 1,3 dicarbonyl.
So I saw this specific one on the test and I got it wrong. Can you go over it too?
Yeah, I'll make you co-host and then you can share your screen and then we could go over that. But before we go over that, let me go over the other 2 types, mixed and intermolecular first, and
Oh.
then we'll go over that.
Oh, I'm looking at the mixed one right now.
Oh, at the mixed one. Okay. We could
Yeah.
go over the mixed one from going over your question first.
Oh,
Right. Let me make you co-host and then you can share your screen. Let me stop sharing mine. Yeah. Most likely this is gonna be a mixed Kaizen concept. I just started with the self one because it's easier to teach first and then build onto the mixed. But we're gonna segue to the mixed now.
what is this one? Am I sharing the right one?
Yeah, I see it. Yeah.
Okay.
Oh, so you chose A, but the correct answer is D.
Yeah.
Okay. So, what did we say the product for Kaizen condensation is? What is the relationship between the 2 carbonyls? Is it 1,1, 1,2, 1,3, 1,4, 1,5?
A relationship?
Uh-huh. It is going to be a 1,3 dicarbonyl. That's always going to be the product for Kaizen condensations, 1,3 dicarbonyl. Right. What that means is that we have 2 carbonyls. That's a dicarbonyl that has a 1,3 relationship with each other. Because you know how this carbonyl carbon here, let's say that's 1. If we say 1, 2, 3, that's going to be a 1,3 dicarbonyl there. Right? Does that make sense so far? Like how that's a 1,3 dicarbonyl?
Yeah.
Right. So let's look at A. We have 2 carbonyls. What is the relationship between these 2 carbonyls? 1, 2, 3, 4.
Oh, that's 1,4.
Yeah, that's a 1,4 dicarbonyl. So that's what the first thing I would look out for these Kaizen products. Always look out for a 1,3 dicarbonyl. Since
Oh.
that's not a 1,3, we could eliminate A.
Okay.
Right. How about B?
1, 2, 3, 4, 5, 6.
1,6. Yeah, so we could eliminate B as well.
1, 2. This one is
Uh-huh.
3, 1, 3.
Yeah, that one's 1,3. Right.
1, 1, 3 also, but the
Uh-huh.
last one is 1, 2. So that's
Yeah. Yeah. So we get rid of that. Okay, so now we're left between options C and D.
And
To predict this product, right? Let's say this is my alpha carbon here. That's the nucleophile. The star atom right there, because the nucleophile is always the alpha carbon of an enolate ion. The electrophile is going to be this carbonyl carbon right here, the dot that I'm dotting right there. Right. When we do this whole mechanism, like let's say there's a negative charge there already, we attack that carbonyl-carbon, pop that double bond onto the oxygen. Let's do that whole connection. Right, so the star has a methyl group, which I drew that methyl group out like that. The dot here is that dot right there. And this is the new bond that I drew over here, new, right there. And it's now attached to a O minus because we popped that double bond onto the O. That dot is part of a six-membered ring, so let's draw that six-membered ring out like that. And then one of the atoms in the ring is the O right there, right? You know how after we get to this point here, we reform the carbonyl, it goes back down, and it kicks out the OR group.
Yeah.
This OR group is part of the chain. So when we do that, that O is not longer there. We could say, let's say this is 1, 2, 3, 4, 5. That's gonna be 1, 2, 3, 4, 5, and then that becomes O minus 2, 3, 4, 5. But then that O minus will get protonated by some kind of H plus to get to your final answer there.
Oh, so when the negative jump down,
Mhm.
take out the O.
Yes, when a
doesn't-
negative drop down, always kick out the O.
So it doesn't directly connect it to the carbonyl that because the
Oh,
kicking is yeah.
yeah. So that kicking down, first arrow here forms that carbonyl right there,
Yeah.
right? And then we broke that bond between this carbonyl carbon I dot here with that O right there, which that bond is no longer there. But you know how I numbered 1, 2, 3, 4, 5? That chain is still there. That's still attached to the O. That chain of the 1, 2, 3, 4, 5 that I numbered is still attached to that O because the 5 atom is still attached to O.
Oh, okay.
Right. Because the O is no longer attached to 1 because we broke that bond between 1 and O. Because you know how before there was a bond between 1 and O, which is this bond right here?
Yeah.
I break that bond off and give a pair of electrons on O like that, which is why there's no more bond between 1 and 5. Wait, 1 and O, right? No more bond between 1 and O. But there is still a bond between 1 and 5. Like, I mean 5 and O. Like this bond between 5 and O is still there.
Oh, okay.
Yeah, that's still there. But we broke the bond between 1 and O.
Okay.
Uh-huh. Yeah.
And then there's one more self, right? Well, you went over self and then
Uh-huh.
next, and then there's intro.
Yeah, intermolecular or Dieckmann condensation. Yeah.
Okay, I'll stop sharing.
Okay.
Okay, thank you.
Mhm. So there's also aldol reaction, which is very similar to Claisen. The nucleophile is also an alpha carbon of an enolate, but the electrophile is gonna be something else. Yeah, well, it's basically the same thing, but we could go over that next time if we have like another session or something. Yeah, because there's also micro addition, Robinson annihilation with the enolate chapter. Let's see. Okay, I'll send you guys these notes too for you guys to review after. Intramolecular Claisen, aka Dieckmann condensation. Okay. Okay. What's your thought process on this reaction here? What's going to be our nucleophilic atom and what's going to be the electrophilic atom here?
That's that ester going to be the one that that ester going the other one going to have the enolate attacking them?
Right. This one here is going to be the enolate.
Yeah.
The ester here is going to be the electrophile. That's the one that's going to be attacked, right? So I'm going to dot this one to show that that one's the one that's going to get attacked, the electrophile. But this is not the nucleophile here because that's not the alpha carbon. We have two alpha carbons here. We could have this alpha carbon or this alpha carbon here. Let's say this is alpha carbon A and this is alpha carbon B. Which alpha carbon, A or B, would give us the most stable ring? Most stable, yeah, ring.
The one with more carbons. So A?
Yeah, A, right? Because if we choose A, right, that's gonna make a 1, 2, 3, 4, 5, 6-membered ring. If we choose B, that's gonna make a 1, 2, 3, 4-membered ring. That's very unstable. 4-membered ring, that's a lot of ring strain. We don't want that. So I'm gonna star this one here. Right. To predict the product faster without going through the whole mechanism, this is what I like to do for intermolecular reaction. I'm going to number this 1, 2, 3, 4, 5, 6, where all of the atoms 1, 2, 3, 4, 5, 6 are carbon atoms. So I'm going to draw that out like that. That's the template of the 6-membered um, atom ring right there. Joseph is reacting to coffee. What the heck? 1, 2, 3, 4, 5, 6. Where 1 is the star atom, 6 is the dot atom. Right. So that is a new bond between the star and dot atom right there. The new bond between 1 and 6, because there was no bond between 1 and 6 before. We made that new bond between 1 and 6 from doing that attack, right? And then popping that up there. In all of these Claisen reactions, always think of this OR group as leaving, right? That's always gonna leave because when we kick it out, like it's not there anymore. The carbonyl on 6 is still gonna stay there. The carbonyl on 2 is gonna stay there. 1 has a methyl group, which is this methyl group right here, which is that methyl group that I drew out right there, right? And this checks out because the relationship between the two carbonyls here is a 1-3 relationship. 1, 2, 3. So that's good, right? If there was like, let's say an isopropyl on 4 and a ethyl on 3, then you just have to draw the isopropyl on 4 out like that and ethyl on 3 like that, right? Which is why numbering this helps, because numbering helps you keep track of all of the groups here, right? So that you don't put the ethyl on the wrong side or isopropyl on the wrong side and you don't flip-flop them, right? If you number them, then it helps you keep track of every single group. Okay. So that's your answer right there. You always get a ring because this is intramolecular reaction, and this is a 1,3 dicarbonyl still.
Okay.
Yeah, and then for these reactions, I recommend numbering them to keep track of every group and not flip-flopping them.
Okay.
Mhm.
And there's also like aldo.
Yeah, aldol reaction,
Yeah, so I
aldol
think there are
condensation.
like different types of aldo condensation also, right?
Yeah, there's different types. There's self-aldol, there's mixed aldol, and there's intramolecular aldol as well.
I always get that mixed up with the previous one.
Oh, the Claisen?
Yeah.
Yeah. I'll tell you how to tell the difference between them and like know which one is going on.
Okay.
All right. So for aldol, the nucleophile is going to be an alpha carbon of an enolate ion. The electrophile is going to be a carbonyl carbon of an aldehyde or ketone. Most likely an aldehyde, right? That's most likely going to be your electrophile, the aldehyde carbonyl carbon. And then the alpha carbon of the enol ion is most likely going to come from a ketone. It could be an aldehyde as well, but most likely a ketone. And we'll go over that when we go over the mixed. Right. In the previous example, the example where we did the Claisen, the electrophile always has to come from an ester. Right? The electrophile always has to be an ester for Claisen. But the nucleophile could be the alpha carbon of a ketone or an ester. Okay, let's look at self-aldol. Well, actually, the products here. Right, you're going to get an aldol if you have no heat, or you're gonna get an enone if you do have heat. Or you might see alpha, beta, unsaturated carbonyl. Same thing. Right. Well, some professors, like even though they put no heat, they just go all the way to the enone, right? Because that's aldol dehydration. If you have no heat, then that's aldol condensation. So it actually depends on the professor, but for the DAT, do they give you heat as well for aldol reactions or no heat? Because I'm pretty sure they do give heat as well.
They gave me heat, but I think they gave me both. Just let me.
Oh, both like no heat and heat as well?
Yeah,
Oh dang. And then does that make it different? Or like if you have no heat, does it like still go all the way down to this product here? Or does it stop at the aldol?
it stops at the aldol.
Oh, okay. That's good to know. That's good to know. Right. Because an aldol is gonna be something like this, where we have an alcohol that is beta to the carbonyl, because this is the alpha carbon, that's the beta carbon.
Yeah, I
Right.
think I got that one wrong before because they give me like that option, but then also the other option, and I chose the other one because I didn't know like the heat and no heat one.
Oh, you chose this option here?
Yeah, because like I think it was one of those trick questions because I don't think they want like a perfect score, so they're throwing in like trick
Oh,
questions for that.
and then they put no heat, and then like this was one of the options, and this was the correct answer here.
Yeah,
Oh, okay.
that was
Dang, I
on my
didn't.
test on the actual one, and then I think I chose the other one, and then I
Uh,
think that was part of the reason why I got like lower score too.
yeah, because usually like it does go all the way here with heat, but if you do not have heat, it stops here, right? And then they didn't give heat at all, so that's why this is the more accurate answer here, because there's no heat, it doesn't go down to dehydration.
Oh,
Yeah. Yeah, because you need heat. You need heat to go here. That's tricky. The reason why I said it depends on the professor, because a class I teach, the professor like he says this is the answer even though he puts no heat. So my professor was like he didn't care about that, but the DAT does, so that's good. That's good to know.
yeah, I think that was like part of the trick questions.
Yeah, yeah. Right. Dang, that's tricky. Okay, so let's look at self. Any base doesn't matter. Let's just use NaOH and water. And let's do the one with no heat and heat, right? Um, okay, so based on what we've been talking about earlier, what do you guys think is the first step of this mechanism? If we have a strong base, what's the most acidic hydrogen here?
Chocolates. The most acidic hydrogens is the alpha hydrogens.
The alpha hydrogen here, right? So we're gonna deprotonate that and generate our enolate ion here. That's the first step. Generate the enolate ion. Now from this enolate ion here, what's the nucleophile? The O minus or the alpha carbon, and why?
Hmm.
Right. What's gonna attack the electrophile? Is the negative charge on O or the negative charge on C more reactive,
On
more nucleophilic?
C.
Yeah, on C, right? Because the negative charge on C is less stable, making it more reactive, right? And since this is a self-aldo, I'm gonna bring in another aldehyde right there, right? So I'm gonna say this is my star atom, which we said earlier because it's more reactive, and this is my dot atom here. I'm gonna reform that carbonyl, use the star atom to attack that dot atom, the carbonyl carbon, and pop the double bond to the oxygen right there. Does that make sense so far? Like all those arrows that I drew out?
Yeah.
And then once we have done that, I make a new bond between the star and dot bond like that. That's a new bond between them. Right. What else is the star carbon attached to that I didn't draw out yet?
Hydrogens? Oh.
Right. Hydrogens are there, but I can still leave them out as invisible. But there's one more group
Oh,
that
that C bond.
CH3, right,
Yeah.
methyl group, which I could just draw out like that. Just move it down like that. Right. Now, what is attached to the dot atom here?
The new one, the carbonyl with the O negative
Uh-huh. Oh, negative.
with
Joseph drinking
the
coffee?
ethyl.
Yeah, with the ethyl, that's right. And then it is also attached to a hydrogen, but we don't have to draw that hydrogen out. We can leave it as invisible. Right? Which like we could say is like right there. Right.
So
Now,
for Aldo and for the other one, what was it? Sorry.
oh, Kaizen?
Kaizen, like both of them has 1,3.
Yeah, yeah,
Oh,
yeah. Uh-huh. Both of them have 1-3 relationship like that. That's right. Uh-huh. But you notice how for this one, there's no OR group to kick out when we go back down. Like
oh,
if we go back down, there's nothing to kick out.
also that's the difference too.
That's the difference. For Kaizen, there is something to kick out. There is an OR. But for Aldo, there's no OR, no S there.
Oh,
And if there's no OR to kick out, what happens next is to proteinate it with water and make it into alcohol. And that gives you your aldol product with no heat. And that's it, with no heat. Like that.
oh,
But we are in heat. So what happens is that the base will come back, deproteinate the alpha hydrogen, make a double bond there, and just kick out that OH. Right? Technically, something else happens before that, but since this is a DET multiple choice question and not mechanism question, I'm not going to go over that. But technically, this is the shortcut way, right? Which is just going to make that double bond right there and then kick out that OH right there, which gives you this enone here, the alkene next to the carbonyl, like that, which is the answer if you do have heat. What kind of leaving group is this? OH. Is this a bad leaving group or a good leaving group?
it's a good leaving group. Is it?
It's bad.
Oh,
Right. Uh-huh. It's a bad leaving group, which is why it stops here with no heat. The reason why it's able to leave is because we added heat. If we add heat, there's enough energy for it to kick out, the bad leaving group. Heat kicks out, kick out, bad leaving group.
wait,
Right. Uh-huh.
can you remind me, like, why is it bad leaving group? Like, what makes it a bad leaving group?
Yeah, let's go over good versus bad leaving group. So the leaving group is going to be better if it can leave with a negative charge, right? If it is stable with a negative charge. So let's say we have this group here with an OH, and we say that's a leaving group right there. When it leaves, right, we have this OH minus right there because you know how always leaves with an extra pair of electrons from this bond that leaves with it. That bond always leaves with the leaving group, which comes as a lone pair right there. Does that part make sense so far?
Yeah.
Yeah, this negative charge here is like relatively unstable because it can't do resonance at all. It's very basic. This OH minus is a strong base. It's very reactive, right? This is very unstable, very reactive, right? And if it's very unstable and very reactive, it wants to go back, which makes it a bad leaving group. It wants to go backwards like that.
Oh.
But if you compare it to something like this and make that leaving group leave, and we get water, is this stable or unstable?
Water is stable.
Yeah, stable because it's neutral, no negative charge. And then that makes it unreactive. So it's able to like stay still. It doesn't go backwards. It stays still, unreactive, good leaving group.
Okay.
Let me give you another example here. Or actually multiple examples. Okay, so let's say these are our leaving groups here. Which one of these are good leaving groups and which one of these are bad leaving groups, right? So imagine them leaving with a negative charge. Which one would be good? Which one would be bad?
BR is good.
Uh-huh. Because it leaves us Br minus. And why is the negative charge on Br stable? It can't do resonance, but why is it stable?
It's electro.
Negative, right? Br is very electronegative, being able to hold the negative charge well. So that's a good leaving group. Nice, nice.
Mm. The carbon, the ester.
The ester, so let's draw that out when it leaves, which is this leaving group right here. Does that look stable or unstable?
That looks stable.
Uh-huh, right, because it can,
Because it can do resonance.
yeah, because it can do resonance, making it a good or bad leaving group.
Oh, if it's stable, then it's good. No,
Uh-huh,
so if it's stable, then it's good living group because
yeah, if it leaves with a stable negative charge, it's a good leaving group. The reason why is because if it's stable, is it reactive or unreactive?
unreactive. Oh, so it doesn't.
Uh-huh.
Oh,
So it doesn't do anything. It stays still. It doesn't go backwards. It's a good leaving group.
and then hydrogens is bad living group.
Yeah. H minus, very, very bad leaving group. Like the worst leaving group. And then R minus.
Mm, that's a bad living group.
Right.
And
Why?
because it can't do resonance and is very unstable. And
Yeah,
it
it can't do resonance and it's very
three,
unstable.
no SP.
Yeah, it's sp3, but Br minus also can't do resonance. But why is this one a worse leaving group than this one? They both can do resonance.
Um, because Br is electronegative, so it wants the hydrogen, I mean the negative to itself.
Uh-huh.
And
Yeah.
the other one is carbon is not as
Yeah.
wanting.
Uh-huh. That's right. Carbon is not as electronegative, making it unstable. If it's unstable, it's very reactive, making it a bad leaving group because it will go backwards.
Okay.
Yeah. So that's the leaving group thing. Right. So that's why if you have no heat, you stop here. Right? Because that OH is not going to leave if you have no heat. But if you do add heat, there's enough energy to kick it out and make this enone here with heat. This one here, uh, right. But if you do have heat, Then you go all the way to this enone. Alkene next to key. Well, yeah, alkene next to carbonyl. Right, alpha, beta, unsaturated carbonyl. Alpha, yeah. Does that make sense so far?
Yeah.
Uh-huh. So that's self. Aldol, let's look at mixed. And I'm gonna give you a mixed aldol that gives you one product because I don't think the DAT is gonna test you for like 4 different products, 8 different products. And I'm gonna have you choose the nucleophile and electrophile. And I'm gonna have you predict the product as well. Oh wait, before we go over that though, I'm gonna show you a trick on how to predict the product without drawing out the whole mechanism, right? So you know how we started with this structure here and we put NaOH, water, and heat?
Yeah.
So to predict a product fast without doing the mechanism, star the nucleophile, the attacking atom, which is the alpha carbon of the enolate, dot the atom being attacked, which is the carbonyl carbon of an aldehyde, most likely. It could be ketone as well, but most likely an aldehyde. Make that new bond between them. Star, dot. That's a new bond. And then you know how the dot used to have a double bond O?
Yeah.
That double bond O, what does it become when it gets attacked?
The O negative.
O negative. Wait, which can become the O negative can become a
H.
OH,
Yeah.
right? And then we
Without
still
heat.
attach, yeah, without heat. And what do you do now to predict the product with heat, right?
With heat,
Like,
the heat going to react with the alpha hydrogens and
uh-huh.
take out the
Mhm.
take out the OH and give you a double bond.
Yeah, and the double bond is always going to be between the star atom and the dot atom, right? And then the OH is not going to be there anymore. It gets eliminated. So when you're trying to predict the product faster, this is what you do, right? Without drawing out all the arrows and mechanism to save time on the test,
Oh.
right? But if you have time on the test, then it's best to go through the mechanism just to make sure you get everything correct. But if you're running out of time, then this is what you do to predict the product faster without doing the whole arrows like this. Does that make sense so far?
Yeah.
Okay. So now let's try that on here. Let's try predicting the product fast with this question without doing the whole mechanism.
You put the star on the ketone.
Right. Which part of the ketone?
Which part? The one
Mhm.
right next to the carbonyl.
Yeah.
Alpha hydrogens.
Uh-huh. Right next to it. It cannot be this one here. You can't say that. That's the star one.
Oh, and
Yeah.
then the other one you put the dot right below the carbonyl,
Mm-hmm.
right at the carbonyl, and
Right
then
at the carbonyl, right?
yeah, and the product. I think the benzene ring's still in there,
Yep. Benzene ring still in there.
and then okay, and at this, I think that would be going up as O
Mm-hmm.
negative,
Right. Which can become a
what can become the OH.
yes, OH, right. And what's the new bond? What new bond? What's the atoms between the new bond?
Mm,
Like what atoms are we connecting here?
carbon?
The star and dot carbon that we started, right? Like you started the
Yeah.
alpha carbon and the dot atom, right? So let's draw that new bond out like that, right? Where that's the new bond right there. The
And,
H here, I'm gonna leave us invisible now.
and there's another carbon, I mean, there's another methyl coming out because there's extra, yeah, and then the carbonyl going up. Yeah, like that.
Mhm.
And
Right?
with
And yeah.
Yeah,
Let's
with
just put
heat
here.
is going
Yeah.
to be the dot with the star, but then there's a double bond, there's no OH.
Yeah. Double bond between star and star, no OH. That's how you predict it fast with the mixed. With no mechanism. Yeah, with no mechanism errors. Right. Does that make sense? Yeah, that's good. That's good. You got it. Well, yeah, I would be careful here. Stop here with no heat. If you don't see that, or heat, or some high temperature, he might give you like, I don't know. Oh, the test might give you like 300 degrees Celsius or 100 degrees Celsius. Like any kind of heat. Not you don't have any of this, right? You stop here with the OH, no double bond. But with heat, then you make the double bond between the star and dot. Nice. Okay, so that was mixed. Let's go through intermolecular now. Okay. I'll have you try this one.
Because the star is right next to the carbonyl on the left. No, right.
Yeah. Right. On the right. It's not on the left because what's the problem here? If you make that the star and make this the dot, what's the problem that you figured out?
Um, I don't
What
know.
membered ring is it gonna form?
Oh, it's gonna 1, 2, 3, 4, and that's really unstable.
Yeah, that's right. And why can't we say this is the star here?
Because there's no
Uh-huh.
alpha hydrogen.
Yeah, there's no alpha hydrogen to deprotonate. We need at least a alpha hydrogen to deprotonate to make a negative charge, right? And why do you say this is the alpha hydrogen, the alpha carbon, and not this one?
Because
Same
it
reasoning
gives
as
you the most carbons.
uh-huh. Yeah, ring. Right. 1, 2, 3, 4, 5, 6. For intermolecular reactions to predict the product, what did I do last time? Once I numbered it at 1, 2, 3, 4, 5, 6.
Or in,
Right. To predict the product fast without throwing the whole mechanism.
oh, to predict the whole thing.
Uh,
Oh, there's a new carbon bond coming out of that star.
And dot, right. And for all intermolecular reactions, it always forms for all intermolecular reactions, it always forms
Inter-
a ring. It always forms a ring,
Oh,
right?
oh yeah, it's always one.
Uh-huh. Because you know how when this attacks itself, it always forms a ring. Like we're making the bond between like the two things here because the nucleophile is on the same molecule as the electrophile, like that. Right? And then when it attacks itself, it always goes around and makes a ring.
Okay.
Right? Where this star is 1, this dot is 6. So this is 2, 3, 4, 5, 6, like that. Now, what's attached to each atom here?
I think there's a carbon bond coming out of one.
Carbon. Yep.
And then and there's a new bond, and then there will be a carbonyl coming. There's a carbonyl that the next to the star on the number 2.
Yeah, on number 2, right? Carbonyl on number 2. Right. Uh-huh.
And then at the dot, there will be OH coming with heat, and there's double bond.
Between
Between 6 and 5. Wait, 1, 2, 3.
right,
Either
so
1 and 6 or 6 and 5.
yeah, it's always going to be for this outer reaction. The double bond is always going to be between the star and dot. So what
It's
are the numbers of star and dot here?
1 and 6.
Yeah, 1 and 6. So it's always going to be between 1 and 6 right there. between
Okay.
the star and dot. Shoot. Yeah, wait, what else? What else?
Oh, that butyl
Uh-huh. So brutal on carbon.
on number right next to the on number 4. On
Great. So on number 4, that is a
oh no no no.
methyl
On
group.
number 6.
Number 6, right? Number 6. Number 6. Brutal on number 6. Now there's one more group missing here.
Number 4
Yeah, number
is
4, which is
methyl coming out.
methyl. Like that. Right. So intermolecular is probably the hardest one to predict because you have to make that ring. And you keep track of every single group with the numbering like that. So that's probably the hardest one, intermolecular. Right. So this is your final answer here with heat.
Okay.
Uh-huh. Yeah. Okay. When is your guys' DAT again? What day?
July 8th.
July 8th. Okay, that's good. Um, yeah. How are you guys feeling about it so far? Like the sections, like OChem, bio.
Um,
Uh,
right now, I think I'm struggling on math the most. Probably.
ma-
Like, it's the math is probably the hardest for me right now. And then chemistry and then OChem, just because chemistry has math in it also.
yeah. All
And then
right.
OChem is better than chemistry because of that. And then mm, I think I'm best in biology.
Yeah. I see. That's good. That's good.
The reading is still like it's okay. Like reading
Uh,
is hard.
How about that 3D thing? Like we have to like look at it and then rotate.
PAT.
Yeah.
Oh my God, that one.
So
Uh,
bad.
it's so inconsistent. It's like my performance is one day is good and then one bad day and then it's like so bad. And it's always on the test day, it's the bad day.
Oh no. Oh no. I'm sorry.
Yeah, so
How big is the OChem section? Like what percentage of the DAT is OChem? Like 10, 8, 20,
um, it actually have the whole
5?
section for it. Like the whole, because for us, it's kind of like individual scores
Mm-hmm.
and then it averaging up, but then they usually look at individual score. So it's
I
out of
see.
like 30, and as
Uh-huh.
long as you
Wait,
get above 20 is fine.
yeah.
And
I
I think
see.
above 20 is like there's 30 questions and it's out of 30. So above 20 is can only get maximum 10 questions wrong.
Oh shoot.
Yeah,
Yeah. And then that's like 20 out of 30, right?
20 out of 30. Yeah.
Oh, okay.
Yeah.
Dang.
I was like, but then I think DAT is a lot more manageable than MCAT because I've seen MCAT
Mhm.
before and oh my God.
Yeah.
Oh no.
7.5 hours, including lunch break.
Yeah, and then you guys reading like for MCAT reading questions is so hard. Like what
Oh
cars?
yeah. Cars, I know.
Cars?
Yeah.
Huh?
Yeah. Wait, that's basically the English section, English section for the MCAT cars
And it was
section.
worse than DAT. It's just like so much harder. I can't.
Yeah. Uh-huh. Yeah, maybe if you guys are down, we could do an in-person session like with the big whiteboards at the library, SJSU.
Yes.
Uh-huh.
Actually, we were supposed to go to the library today, Milpitas
Uh-huh.
library, but I bailed on Tiffany.
Yep.
Oh, yeah,
He's
Joseph failed.
bailing on me
He was.
on Thursday too.
Did he sleep? Did he
No, on
oversleep?
Thursday, I think I'm busy because I have some meetings that I need to do.
Oh shoot!
But
Did you
yeah,
guys meet
I
up
was
yet?
sleeping.
Oh no.
It's because like I had to wake up early to check on the lizards, and then I was just so
Uh,
sleepy that I just wanted to,
oh yeah, you didn't want to
yeah.
go. Did you go, Tiffany, or did you just like stay home and study?
I ended up staying home and studying, but I had to wake up early too on like
Uh-huh.
today. But then not
Yeah.
checking on the lizard. I was just like playing tennis. for the whole time.
Oh, I see, I see. Yeah, yeah. Yeah, we gotta do an in-person session, like three of us, like soon before your test.
Do you live in Davis right now or like here in
I
San Jose?
graduated from Davis recently this quarter, so I moved back to San Jose. So
Oh,
I'm staying in San Jose now.
oh, okay, okay. So you're gonna go
Uh-huh.
to school around here? Is it the
Yeah. Hmm.
chiropractors?
Yeah, but the chiropractic school is in Hayward, so I'm just gonna drive there, 30-minute drive.
Oh, like isn't that close to East Bay? Am I tripping?
Is it Jose Joseph?
Is it close to
Um,
East Bay?
I think so, because CSU East Bay is in Hayward too.
Oh yeah,
Oh,
yeah, so if it's in Hayward, then it's pretty close.
But I
oh.
think it's actually closer than CSU East Bay.
Why did you want to switch from like medical and stuff to chiropractor?
Yeah, why?
So I worked as an EMT for 6 months at college, and then I saw a lot of patients with musculoskeletal injuries, and then I was interested in it. So I did more research. There was also PT, physical therapy, but the chiropractic program that I enrolled in has a PT program involved in it. So I um, researched more about that, and I went to the Discovery Weekend with Joseph actually, and then that made me more interested in becoming a chiropractor. So I want to do chiropractor now.
Oh, you didn't like the work that doctor do and stuff?
Yeah, well, it's valuable and like I appreciate it, but I don't think I want to like sacrifice so much. It's like too much for me. Right? I just wanna do the chiropractor and do the outcome tuning business.
Oh, okay, yeah, I get that
Yeah.
because I was
Yeah.
actually moving a lot from like I was like nursing and then I went for like
Uh-huh.
I think I want to go for the medical school and I was
Yeah,
like
yeah.
too much. That's like my whole life studying.
Uh-huh, yeah. I
And I
know.
was like,
Like
I don't think I like that because I like traveling and everything too.
yeah. And most of my friends are pre-med. They're taking like 1 or 2 gap years before applying it. I don't wanna like, take gap years. I just want to go straight to it.
Oh, you just want to go straight to like school again
Yeah.
and finish it?
Yeah, and then finish it. Yeah, that's what I'm doing. Like this summer, like I'm going back to chiropractic school.
How
July,
about that
I'm
was my plan?
starting.
But
And
that
then
was
now you're
your
taking a gap year.
Yeah, but this wasn't planned.
Yeah, this
This
was the
gap year
plan.
wasn't planned.
No, he was
Uh,
like last semester, he was just like out of nowhere. He was like, okay, I'm gonna apply for chiropractor. And then he applied for it. And I was like, are you crazy? Yeah, and then he was just like, it's super last minute. And then he also applied for dental school and chiropractor too. And I was like, oh my God.
I pushed back my start term for chiropractor school though.
Oh, wait, you push back?
Yeah, because I was supposed to start this summer, but then I told the admissions next summer. But I don't think I'm gonna I think I'm just gonna stick with dental all the way.
Yeah. Yeah. I support that.
And his headset died.
Oh shoot. I forgot my headset was connected to my iPad and my mic was connected to the iPad. Uh
Oh,
yeah, I didn't hear you guys. Uh wait. Did you hear the question? Were you planning to take a gap year after college or were you planning to go straight through?
oh, me?
Yeah.
Oh, I'm already taking my gap year because I was supposed to graduate last semester, no, last year, last summer.
Mm-hmm.
But then since I changed my major from nursing to like biochem, and it took me like one extra semester, so I technically took my gap year. Yeah.
Uh I see, I
So she
see.
graduated with me.
Uh-huh. I see, I see. Dang. And are you guys applying at the same time?
Yeah.
So for the next cycle? Dang.
Yeah.
What's your dream dental school? Like I know Joseph's is like UCSF, right? I
Oh,
think.
mine is
I think
either
mine is
UCLA or
UOP now.
Michigan.
Oh, I see. I
Yeah,
see.
because I kind of want to go out of state just to see what it's like out there.
Honestly, yeah.
But
That's
I think
good.
Joseph is like either UCSF or UOP because he want to stay close by.
Yeah.
Yeah. Dang. That's
Yeah.
interesting.
Yeah, but if I can get into UCLA, I think that's my dream school, UCLA.
UCLA, yeah.
Kind of competitive here, so
Muhammad went there, right?
Oh, he's
yeah,
going there.
he's going there right now.
Oh, wow. Like one of my UC Davis friends, he was also an organic chemistry tutor, Andrew Tran. He's going there too with Muhammad.
You're so smart. Oh my God.
Dang.
What?
Yeah, yeah, and he graduated the same time as me, like this quarter.
Oh, you haven't
Crazy.
graduated yet?
No, I did.
Oh, you
Like,
graduated early. Is that what it is?
like on time. Like I graduated like 4 days ago.
Okay.
Yeah, yeah, yeah. Like 4 years.
Oh, wait. Oh, okay. Yeah.
Uh-huh.
Yeah, that's I wish
I
I
heard you were an Occam tutor too. Like that's what Joseph told me.
yeah, I forgot everything. Like
Oh, it's
Oh,
true.
I totally
I
forgot
was in
that
the
Tiffany one.
I was actually don't when I was tutoring, I'm so bad at teaching other people just because like a lot of the concepts I learned, it makes sense to me, but it doesn't make sense to other people because yeah, it's just like that. And then I also learn from my past tests instead of like the actual concept. So I just learn what needed for the test.
Uh-huh.
So that's how I did well on the test. And then when they asked me like a questions around the test, I could not answer it.
How do you react to that? Like what do you say to them? Like, oh sorry, I forgot. Let me check your notes or let me get back to you. How do you deal with that?
I actually studied with them. I just sit there and I was like, okay, let's study this together.
Oh, that's good. That's good. That's actually a good way to respond to that because the student actually sees how you study, and that's an important like thing that they know too.
Yeah,
That alone, you know.
yeah, but I wasn't like at you guys' level of like able to answer all the questions. I just told them exactly what they need to know for the test,
Uh-huh.
just to like, because a lot of time you don't need to know too much. That's what I think.
Yeah.
But for this test, it's different. Like it's like so random the questions.
Yeah, they that's good.
Yeah, so that was. But don't yeah, don't rely on me on that because I forgot basically everything.
Oh no. Were there other tutors there when you were working as a tutor, or was it just you tutoring students?
Oh no. There was like four other people, but I'm mostly in charge of grading the paper and test. And then other people they do office hours because yeah, I soon realized I'm not a good teacher. So I
Oh, so you're one of the graders, like to help grade the assignments.
yeah, I help grade and then like also proctoring most of the time.
Oh, yeah,
Like
that's
my
good.
professor let me do a whole office hour one time, and I was like, I told him I was like, that was so bad. I don't think you should do that again.
Oh, really? Wait, your professor said that? Oh, he actually said that?
No. I told him I was like, that was so bad. Don't let me tutor people again. Like,
Oh,
I
I
can
thought
like do
the
all the
professor
grading. So
said
I
to
just pick
you
up
like
all
you were
the
so bad.
yeah. I just told
Oh,
him I was like, I'm so bad at this. So I just pick up all the to make up for it. I just pick up all the people like grading
yeah.
instead of like them coming in. I just took out all the hours to make up for it. And I just like, okay, I'm gonna grade for you guys. You guys do practice like office hours, please.
That's good. That's good. That's pressure on you. Do you remember me going in person to tutor like Joseph, Yvette, Christine, you, and like some other people, like a whole group that Joseph invited, like
Oh
that
yeah,
one
Yeah.
time you guys
Martina,
just studied for
Cindy,
outcome.
Selena, Rafa.
But one time in the library,
Yeah,
remember?
the library with that room. Yeah,
Yeah, I went one time. That's why I was like, I texted him at the beginning. I was like, is that the same guy that came to the library before? And then
yeah.
he was like, oh yeah.
Oh, you texted him that like today?
Yeah,
For this?
I texted him. I was like, is that the same guy? Because because I remember your face. I was like, is that the same guy?
Yeah. It's me.
But I didn't know you
Feels so
graduated.
much since then. Like back then when I first tutored you guys, like I was like still. But that was like 1 year since I've tutored. But now I'm in like my 2.5 years since I tutored. So I improved a lot since then.
Oh, I think I forgot everything instead of improving.
Oh no. Well, that's because you dropped OChem. Like you didn't like touch it since then. But like I
Oh
like
yeah,
see every day.
Yeah, at Garfield Live after Ocam that I did not touch it until now that I kind of regret. I should have just do practice problems so I like just for fun, but I didn't do it. Yeah, so no.
Yeah, I see, I see. Well, I'll see you guys next time. Let's plan that in-person study session at the library, like some library with the whiteboards, and then we could do more study plans on OChem.
Okay.
Uh-huh.
Thank you so much for today.
Yeah, no problem, no problem.
Thank you.
Yeah. Bye.
Good night.
Bye.
Night.
Charming.
Tommy.
Fortnite.
Fortnite. Okay, okay.